How's everyone doing? So you survived PA1 and lived to see another day, which is awesome. So I did peek at some of the chatter last night or this morning on Discord, and I just got to say it's like really cool that like you're got a community of fellow students and you're actually like helping each other and stuff like that. That doesn't always happen, right? It tends to happen at Clark. It doesn't always happen at other schools, and it's like really cool that like you know, you're willing to share your knowledge and help one another. And like I say, helping people solve their problems is a really great way to improve your own skills. So that's always awesome. So really good job on PA1. Almost everybody managed to create the repo, push their code over there, and then give me access to it. A few cases where that did not happen, and if that's the case, I sent you an email with some suggestions on what to try and what the problem probably is. So if you got an email like that and you haven't already corrected this, and you don't know what might be wrong, please talk to me, okay? You can catch me a few minutes right after class today. And if you take care of this like right away, then I can grade it with the other assignments this afternoon. All right, so pass around the assignment sheet. Okay. And PA1 is behind us. We'll go through code on Monday and look at solutions for that. And the bit with get is similar to what you're going to see. It's exactly what you're going to see with all the other assignments in this course, and 222 and probably 223. So it's painful up front and kind of weird, but once you're used to it, it becomes second nature, and it'll serve you for the rest of your time here at Clark, and probably at WSU if you're going there or wherever you're going. So it's time well spent, even though it can be frustrating. So any questions? I want to talk about a bunch of sort of random sounding stuff today. I want to go over some more Git commands, some Linux shortcuts, customizing your Linux environment, stuff like that, and work our way back towards talking about C next week. But any questions before I launch into all of that? Yeah?
How do you use scrolls?
How do you use scrolls? In what?
Rogue.
Read. R.
No freaking way.
And be careful with scrolls.
What do they do?
Some are very good and some are very annoying. So some people always read scrolls and quaff potions up front.
You do what with potion?
Quaff. Q.
What's this game?
Rogue.
On Linux? Is it on the server?
Yeah, it's on the server. And it's a good way to practice HJKL movement and VI. Yeah.
Holy crap!
Call functions in Bash because I trained.
Yeah, so in Bash, if you spell it right, function my code. Right, so if you want to call it, just type in the name of the function.
Okay, yeah, I just did something wrong.
Okay, and if you put arguments after it, you can pick those up with $1, $2, and so on.
You don't have to pass a value over parameters.
You don't have to, but you can.
No way.
That's right.
Right, so. All right. This time with visual elements added. So my code was just a function. My code prints out an echo and it does a date, and if you say my code, it runs it. Function show says echo, you pass the parameter, and it prints out the value of $1. So if I say show hello, it says you pass the parameter, and $1 is equal to hello. Mm-hmm. So other questions? So Bash is quirky, right? It's picky about syntax. Not quirky. It's picky about syntax. but it can be really useful. Okay, it's really good for rapid prototyping. If you just want to do something, you don't want to write C code, you don't want to initialize variables, allocate memory, stuff like that, you can do a lot with bash. And just throw together a script, make it executable, run it, and you get a lot of firepower out of a few lines of code, right? It's got the functionality of C in terms of looping and conditionals and so on. It's got a lot more functionality that we're still going to talk to, including things like associative arrays, which is a really, really powerful construct. It's also got the full resources of Linux, right? I can say sort with the name of a file, and it sorts that file alphabetically. And if I want to sort a file inside a bash script, I can just say sort file, and it'll sort it. And if I want to put the output of that sort into another file, I can do that. And all this stuff that we have available inside Linux system, we can run from a bash script. And that's really powerful, right? There's tons of things you can do with that. And you can write a C program, and you can run that from your bash script if you need to do something more nuanced. So it's a very powerful environment to work in, and it's so quick to develop. Once you get past the, if space, bracket, bracket, space, blah, 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 dash EQ, that kind of stuff. So let me just give you an example. So you submitted PA1, right? You pushed it over to the repository. And in homework 1, you did a submission on Canvas also that gave me your Git user ID, right? So if I want to download your PA2, what do I have to do? I have to go to your homework 1. I have to look up what your Git ID is. And then I have to make a directory with, that I'm going to grade your PA1 in. Go into that directory, say git clone git at gitlab.com : your Git ID / PA1.git, and then go into that directory and so on. And I have to do that 62 times, right? That's, a couple of hours worth of work just downloading your projects, right? So I have a script called git clone. And to run this, all I have to say is git clone space PA1. And I walk away and I come back in 5 minutes, and all of your projects have been downloaded into individual directories, and each directory has the name that you have in Canvas, and there's a PA1 directory under that, and that's got all of your code that you pushed into GitLab. And there's very little in here that we haven't already gone over, right? I set up some symbols for my working directory. I have a flat file that I made after homework 1 that has 2 columns, your Canvas name and your GitLab ID. And after doing some initial checks to make sure that I specified a project name and stuff, I basically just do this while, and it's a while read line statement which ends with done less than Git IDs. Well, this is a way that we can read lines from a file, 1 line at a time. And for each line, I use this command sed, which we haven't talked about yet, but we will. Sed lets me break up a line based on spaces or patterns of characters. So this basically lets me break my line into 2 pieces, your username and your Git ID. And I print that out so I can see it while it's running. And I check to see if I've already made a working directory with your username. And if I haven't, then I go ahead and create it. And then I check to see if your Git ID is available. And if it's not, I print an error message. And I also save that error message in an error file. Now, everybody has done homework 1 at this point, so I have Git IDs for everybody, so I don't get errors here. And then I basically go into this directory that I made above with your username in it, and I use this git clone statement, which we're going to talk about shortly, to pull down your repository into, in this case, a PA1 folder. Anytime we do a command in Linux, we can check this variable $? That tells us if our command succeeded or not. If it's a 0, it means the command succeeded. If it's not 0, it probably means something went wrong. So after I say this git command, I check $? If it's equal to 0, it was a successful download, and I bump up my number of successes. Otherwise, I say I can't read the project for this user with this git ID, and I put that into an error file. And then when I'm done, I say how many times I downloaded successfully, how many times I tried to download it, how many students didn't have a git ID. So at 8:20 or something this morning, I just said git clone space PA1, made breakfast, came back, and I had 56 PA1s sitting under directories with each of your usernames. And then later today, I'll take that, put it into an archive, push it over to the test account, and then I'll just start playing stick games all afternoon. Right? So this, it took a few minutes to write this. Okay, actually it took about 20 minutes to write this. But now I can do all these things that I would normally do by hand in Bash by just typing one command. And that's nice. I also have a command called git ID. And when I'm sitting in one of your user directories, I can type git ID and it shows me your git login ID. So if I want to pull down a late submission or check an individual file or something, I can find your git ID by just saying this one command, instead of going back to my file and looking for your name and finding your git ID in there. And that's just another script. So this is all just taking these tools and putting them together and coming up with basically new tools. So scripting is nice, right? It's quick to do once you're past the syntax oddities, and it's potentially very powerful. It's also very error prone, right? You put a space in the wrong spot and maybe your script crashes, maybe it does something weird, maybe it deletes all your files. So it's not as safe in some ways as a compiled program. It's also not as fast, right? So when you run a Bash script, you have a program called Bash which is running, and that program is reading the lines of your Bash script and interpreting them and deciding what to do. And so this is a way to think of code, of languages. We have sort of two types of languages. Thank you. Languages that are compiled and languages that are interpreted. So when we compile a C program, we have a file.c. That's the human readable version, right? And we run gcc, and this turns into something called file.o, and that turns into something called a.out or file.something or whatever. But an executable file, which is a bunch of ones and zeros. And when we type the name of this file from the command line, this set of ones and zeros gets loaded into the memory of your machine. And the CPU is told, hey, go to this location in memory and start executing those instructions. Okay, so you're running at kind of the lowest level of the hardware. You're actually making a bunch of ones and zeros, pushing them into memory, and then the CPU says, hey, start executing the instructions at this location. And it just reads the binary out of the memory and does what it says it should do. So if you've done Engineering 270, right, increment file register 17 is a 1101 blah, 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 right? That's the stuff that your program got turned into. And you kind of hit the big reset button and it starts executing those instructions. So you have to compile your program and do some other things that GCC does. But once you've got the binary code, that just runs directly on the hardware. An interpreted language is different. You have, your script, stick, and you've got a program called bash. If you're on Cygwin, it's bash.exe, but it's an executable program. And it looks at this file and it reads the first line, and it reads the second line, and it reads the third line, and it decides what each of those things is supposed to do. And when it reads a line that says n equals 20, somewhere in here it's got something that it's going to use to store the value of n, and it'll put a 20 in that spot. So maybe it's got an array that it uses to store variables. And when it sees something like n equals $sign for n plus 1, it'll read that value of n, it'll say, oh, I'm supposed to add 1, it'll do that, it'll get the 21, push that back in there. So it's interpreting your human readable code. And this never gets changed into a machine-readable thing, right? It's just reading these plain statements that you've written and deciding what it should do. And how does bash execute? Well, bash.exe is, a bunch of ones and zeros, and that gets loaded into the memory, and the CPU is executing this program. This program is interpreting your script. So it's slower, right, because you've got this level of indirection running, but it's also a lot more flexible. This is why we don't have to declare variable types, because this is powerful enough that it can say, oh, I equals 7. Okay, well, I've never seen I before, but I guess it's a variable, so I can live with that. You can't do that in the binary code. The CPU is very, very, very primitive. You got to tell it exactly what it's supposed to do every clock tick. Bash interpreter, or any interpreter in general, much more flexible. So Matlab is interpreted, right? If you play with Matlab in 120, that's an interpreted language. It gets weird when we talk about Java, because Java is compiled, but it's not compiled down to the level that you can put it into the memory and run it with the CPU. It's compiled into a different set of ones and zeros that we call bytecode. And the bytecode doesn't run on the CPU. The CPU doesn't know what to do with that. The bytecode is interpreted by a virtual CPU, something called the Java Virtual Machine, or JVM. So the JVM is an actual executable that's running in your memory, being processed by your CPU, and the JVM is interpreting the ones and zeros that your Java code got compiled to. So it's also a layer in between, but because this has been pre-compiled, if you have 5,000 lines of comments, that doesn't slow your program down. If you have a script with 5,000 lines of comments, the interpreter has to go through those to get past it to get to the next instruction to execute. So it's kind of a hybrid between compiled and interpreted. And the space gets really weird, yeah.
So when you said line, does that have a difference between an individual each separate line as compared to using a semicolon and putting it the next code next to it?
Probably be slightly, maybe not.
There's no difference
It
between.
would be minuscule if there is.
So there's not a real point to really try to compact your code.
No, and really none of this is, because really when we're writing bash, we're not worried about efficiency for the most part. Like my git clone thing, right? The slowest part of that is going through the network and going to the repo and pulling the files down and doing all this data transfer. And the time it takes to get through a block of comments or go down to a next line or something is minuscule compared to that.
Would that apply to C?
So C is compiled, so all your comments are gone before you get to the ones and zeros. Your long variable names make no difference because they don't exist. They're just changed into memory addresses. Right? So compiled language is pretty much the style of your code. And at first order, it doesn't really affect that. Now, if you have a really, really rudimentary compiler, there's things you can do when you write your code that'll make the code more efficient. But most things the compiler will figure out now, like what should be a loop and so on. And bash might do some pre-processing that I don't know about that gets rid of blocks of comments or something, but as far as I know, it doesn't. So this is kind of a weird little schism, right? When is something actually running on hardware and when is it actually being interpreted? And it gets even weirder. Starting in the 50s, people started making what were called microcoded machines. And in a microcoded machine, the ones and zeros that are being processed by the CPU, that's not actually what the hardware is processing. The CPU actually has a smaller CPU inside. And that smaller CPU is actually interpreting the ones and zeros, just like bash is interpreting our bash commands. And so even when you're down to ones and zeros being executed by the CPU, that may not be actually happening at the hardware level. It's possible that's just interpreted. So a microcoded machine, slightly slower than a non-microcoded one, but guess what? You can change the instructions on it. Just like by editing the bash program, we could change the syntax of our bash script. Right, we could get rid of the need to have spaces over there by changing what bash does. Well, on a microcoded CPU, you can change what the ones and zeros do. You can say 1001 is no longer an increment instruction. It's now a decrement instruction, or an increment by 2. Or you can make a new instruction. And so what is actually hardware and what is software is not so clear anymore. Right? Hardware used to be the stuff that's hard, the stuff that can't change, and software is the stuff that's malleable, the code. That distinction is nebulous at best now, which is kind of cool. All right, on to PA2, because it's been a while since you've had a programming assignment, right? So we're just going to keep going with the stick program. You're going to do the stick program, but you're going to write it as a C program. And I have made some significant changes to the requirements of the program, so you want to make sure that you make note of these and ask questions if it's not clear. First change is it's written in C, right? Second change, the user always goes first. You no longer ask who should go first. When you play PA2 stick game, the user gets to go first. Next change, the user might not be well behaved. It might be your cat walking on your keyboard while you're out of the house. So the user might type in, a legal number, an illegal number, a word, a series of words, an asterisk followed by 3 question marks and a $sign. Anything goes. Okay, so if you ask the user how many sticks do you want to play with, you can't assume they type in a legal integer. Okay, they might type in something weird, they might just hit enter without typing anything at all, and you need to handle all of those cases. Okay, we're going to talk a lot next week about how to do that, and we're going to have ODPs to help us develop pieces of code to deal with these kinds of things. So we're going to do aggressive error checking. When the game begins, there's going to be 2 ways that the user can specify how many sticks they want to play with. So one option is they can say stick and hit enter. This is my symbol for enter. So they can say stick and hit enter, and your program should say how many sticks do you want to play with. And the user types in, 25 and hits enter. And then you go ahead and you play the game. So the same thing as PA1. The other option, though, is the user can say stick and type in a number on the same command line. Okay, so this is a command line argument. This is a programmer runtime argument. So on the command line, they can say stick 30, play the game with 30 sticks. Okay, so if I say stick 30, enter, the game should start right there. You don't have to ask who's going first. You don't have to ask how many sticks.
You want us to confirm it?
Nope, definitely not. That would be good practice, but no. All right, so that's the next change. 2 ways to specify the number of sticks, on the command line or once the program starts running. If they use the command line, they can only have 1 argument here. And it's got to be a valid integer, and it's got to be at least 10. So if they say stick 5, that's not legal. If they say stick -2, that's not legal. If they say stick 30, haha, that's not legal because they put 2 arguments on there. So if they do this, it's got to be stick and then 1 legal integer, at least 10. Or they can run it by just saying stick with no arguments.
So if they run stick, number, and then help or a random other argument, do you want us to
That's
ignore
illegal. No, that's illegal.
it? So do you want us to not run the program or just
And
figure
yes,
it out?
so if no command line arguments are present, if any errors are detected in choosing the initial number of sticks, print an error message and exit. They don't get another try. Say learn to read and just return. All right, so this is completely different from PA1 because I want to give you a chance to follow a different set of specs. The gameplay itself is exactly the same. The main loop, the mod 4 stuff, all of that's going to be just translated from bash. But the setup and the error checking, right, this is a different spec. So for that part, forget what you know from PA1. So to determine the number of sticks to start with, either a command line parameter or program input. The initial number of sticks must be at least 10. The executable program has to be named stick. I don't mind what you call your .c file, but I would suggest calling it stick.c. But make sure the executable is called stick. Alright, once you start playing, first thing you're going to do is ask the user how many sticks to take, because the user goes first. They put in a number between 1 and 3. It's got to be a legal integer between 1 and 3. Okay? They could just hit an enter without typing in anything. They could put in a negative number. They could put in a 0 or a 5 or ha. Any of those are illegal. Okay? If they put in an illegal entry, tell them that that's an illegal entry and then ask them again and keep asking until they get it right. So we don't kick them out after 2 tries. Right? So that's another difference. They can keep putting in funny numbers all day and it'll just keep asking them. Enter a number between 1 and 3. Alright, and then push it to GitLab as PA2 uppercase and make me a reporter before the due date, which is 2 weeks from today, and you're good to go. Yeah?
Can we use get character, or does it have to be?
You can use getChar, yeah. And we're going to talk about the details of this next week. We're going to go through different ways to do input and parse input and so on and so forth. And I say, for example, don't use A to I, the function. We'll talk about the problem with that. You don't want to use scanf. You want to use scanf. We'll talk about why that is. And how to use getChar or fgets. Alright, so suggestion, you want to modularize this process as much as possible. You want to break it into small pieces, develop the small pieces, and then put them together into bigger pieces. Okay? You don't want to try to just write your whole program from start to finish and get, 100 lines of C code and then try to compile it for the first time and then see if it works. Okay? That's a hard way to develop code.
Do you want us to comment and all that?
Yeah, everything's got to be commented. And comment block in the beginning. So a modular way to develop this would be, for example, you might just write this inner gameplay loop first. Right? Forget about all the error checking, forget about all the options, and just do something like this. Sticks equals 25. So ask the user for the number of sticks to take, which is n. Sticks equals sticks minus n. CPU equals sticks mod 4. If CPU equals 0, CPU equals 1.
Can we move the mouse?
Sticks equals, yeah.
Sorry.
That's okay. There's a basic gameplay loop. Ask the user for the number of sticks to take, subtract that from n, subtract that from the number of sticks, and then calculate the CPU's move by looking at the number of sticks left, taking out modulo 4. If that's equal to 0, set it equal to 1, because you can't take 0 sticks. And then subtract that from the number of sticks. And maybe in here, print sticks. Okay, this by itself will let you play the game with 25 sticks. It may not exit correctly when the game is over, because the while loop at the top exits when it's 0 sticks left, and if the user wins, it's not going to exit until the computer moves. But it will get the guts of the gameplay going, right? It'll ask you for a number, it'll subtract that from the pile, tell you how many are left, it'll make a move for the CPU, subtract that from the pile, tell you how many are left, and it'll keep doing that. So this is a starting point, right? It's not the finished program. It needs some tweaking, but it gives you something to write and something to play with. And then you start embellishing, right? So what do you have to do after this? You have to let the user specify how many sticks. Well, if you don't like dealing with command line arguments, forget about that for now. Just ask the user how many sticks, have them type in a number. Forget about error checking. Assume they're going to put in a reasonable number. So now you're working with fgets and scanf, right? And then, you know, maybe throw some error checking down here. See if the number they put in is actually an integer between 1 and 3. And then maybe, instead of just printing the number of sticks, print a pretty picture. Your pipes followed by the number in parentheses. And we have functions in C. They're full-on functions. We can pass things to them. We can pass things back from them. We know how to do this from 121, right? So I can make a print sticks function. Instead of printf, parentheses, quote, %d backslash n, unquote, comma, n, I could call a function print sticks, parentheses, n. And inside that print sticks function, I might just print the value of n, or I might make a for loop that prints a bunch of pipes followed by an n in parentheses. Right? But I bundle that behavior into this separate function, and I don't need all of this to test my print sticks function. I can make a main program that says print sticks 5, print sticks 7, print sticks 2, and just make sure it showed me 5 sticks, 7 sticks, 2 sticks. Once that's done, right, this is just a function call. And I don't have to worry about that code anymore. I don't have to look at it. It's not cluttering up my loop here. Right? Same thing with getting the number of sticks. I can make a function called get number of sticks user wants to play with. And it returns an integer, which is a valid number. And that can, you know, print out the instructions and say enter the number of sticks, and it can check to see if it's legal. And if it's an illegal number, maybe I return 0. And so after I call my get number of sticks user wants to play with function, I just check to see if the return is 0. If it is, I know they did something illegal, I just exit. Otherwise, I set sticks equal to that, and I start playing the rest of my game. So you keep embellishing, adding, polishing your code, right? But if you start with something that runs and does some level of useful behavior to you, right, it's generally a whole lot easier to modify and add to that than to, you know, be staring at the blank editor window and not sure what to type. So you can start with a minimal gameplay loop. You can start with a print sticks function. You can start with a thing that reads the number of sticks. You can start with trying to get a valid integer, 1, 2, or 3 from the user, and turn these into functions. So the ODPs will help with this, right? This is exactly what the ODPs will be next week. But break it down into pieces and start building it up. Now you already know the algorithm basically because you did this in PA1. So you don't have to work too hard on algorithm development. So does that make sense? Now we'll start talking about C next week, but you should know, you've probably learned enough C. You may not remember it, but you probably learned enough C to do a lot of this already. You may have to dust off notes or go to a reference. But should be enough in there to get started, if you like. All right, good on that? Talk about get. So, we've been playing with get using a very, very narrow set of options. Basically, get init and get remote add origin to do your one-time setup. And then really all I've suggested is get add, get commit, get push. Just cycle through those 3 commands every time you have changes to push over. That's good for a first order, but we can do a lot more with Git. And also, if we get into trouble, sometimes it's useful to know how to do more with Git. So let me make a area. So what should we call our Git repo today? I can't type the spell sound. Shebang. I don't know how you spell shebang.
That's how you spell it.
That's how you spell it?
Yeah.
Okay. think you're right.
There you go.
All right. All right, so we got a shebang.
Oh my god.
Yeah, it's still mission.
Wait.
All right, so I've got my my project built, and I've got 3 files, and I've got a README, okay? And I want to put this under Git control. Okay, so I do my one-time setup for a project. I say git init. That creates an empty repository, and you only need to do this once, okay? You don't need to do it every time that you're doing something in your repository. It just makes that Git area. And then you need to do one-time git remote add origin, git at gitlab.com,
Can't land?
colon username / shebang.git. All right, and that only happens once. If you try to do it again, you get an error message. This is creating that association between your repository and on your machine and your repository in GitLab.
I didn't have time to check it last night, but does that create the repository?
That does not create the repository. It's just saying this is linked with that, but that doesn't exist yet.
So you have to commit, like, at
So you have
least
to
something.
commit, and that first time you do that, that actually makes it.
I did a thing, so you know how you're supposed to do -m and then comment it?
Yeah.
But I didn't do the -m and it brought me to the next page.
Mhm.
What do I do after I comment it in the next page?
Just exit.
Colon
Just
X?
save it, yeah, or colon WQ.
Oh, that works.
Yeah.
Okay, my bad.
Yeah, just save it and then exit.
Okay.
If you don't save it, it says you didn't leave a message. I'm not going to commit.
Okay.
All right, so this is the one-time setup. We never have to do this again for this project. So I've got some files in here. Let's add all of those. Let's git commit. Initial check-in of my code. All right, so I've got 4 files checked into Git on my local machine. Now it's not on GitLab yet, so you have to push it over. So git push origin master. And it will use the thing that I said when I said git remote add to know where to push this, and it pushes it over to GitLab.
Can you remove specific files from the repo through your...
Yes, I'll get to that in a sec.
Okay.
All right, so I've got a clone of my project over at GitLab. Okay, so I forgot about this 4th file, so let's add file 5. Git add file 5, git commit, adding another file, git push origin master. Alright, so we're off and rolling now. And anytime I do work on my project, git add, git commit, git push, so we're on the repo. Okay, so sometimes it's useful to be able to work on your project on more than just the Linux server, right? So you're going somewhere without internet access, and I'm going to have my laptop, which has Linux on it, but I don't have access to linuxengrcs.com. It would be nice if I had a copy of my shebang project sitting over here on my Linux machine. I don't, right? There's no such file there. So here's what I can do. I can make a clone of my project from GitLab onto my local machine. It takes one command, git clone, git at gitlab.com, colon username / repo dot git.
Shebang within E. It's an A.
It's an
He
A.
changed
Oh.
it.
So now, if I say ls shebang, I've got a directory under here. I can go into there, and there's all my work.
By the way, we did look it up, and it is shebang.
Oh well, it's shebang now. All right, so this is great, right? Let's
Another file.
make another file. Let's edit my README. with a typo. All right, so I'm editing on my laptop here, okay? I'm not on the Linux server, so the Linux server has the old version of README. GitLab has the old version of README. I'm just making changes on my local setup here. Here's what I want to do. Git add, README, git commit, git push, origin master. Okay, so now GitLab is in sync with my laptop. Linux server is still out of sync. Let's go back to Linux. Go into my directory. My README's out of date, it's the old one, right? I want to bring this in sync with what's in GitLab, so we have a new command now, git pull origin master. And it says one file changed, README. And now if I look at the README file, it's the one that I had written on my laptop. So what are we doing now? You're working on a machine, you make a bunch of changes, push it over to GitLab. When you want to synchronize another machine with GitLab, go to that machine and say git pull origin master. So pull comes from GitLab and pulls it down into your local repository. Push takes your local repository and pushes it to GitLab. Make sense?
So will that, like, if you have a file in a directory that's not included in your repository and you pull, will that delete that file?
It won't delete it. Yeah.
Does it ever become anything besides origin?
Yeah, but not for me.
Oh, so if I was to create two git in the same.
So if you start making branches, then these things change. Yeah. And branches are another topic.
And do you have to have git initialized to do a pull in a directory?
You have to be in a Git repository, yeah, and it has to be associated through a Git remote add origin, or it has to be something you created with git clone. So either way, it'll get you there. So if your project exists on GitLab first and not on your local machine, use git clone to pull down a copy of it. If your project exists on your local machine but not on GitLab, do the git remote add origin, and then your first push creates it at GitLab. So file 5 should have been named file 4. If I just rename file 5, I'm going to create an inconsistency in my Git repository. Because Git thinks that there's a file 5. If I rename this to file 4, I don't have a file 5, and I have this weird file 4 that it's never seen before. So when you do moves or deletes, you need to tell Git about it. So instead of saying move file 5, file 4, I can say git move file 5, file 4. So that actually renames file 5 to file 4, but now if I say git commit, it's committing this change where I renamed file 5 to file 4. And git push origin master. Right, so I'm all set here. Now my laptop copy still has file 5.
What's your repo?
So if I come back here and I look, I've still got file 5, but if I say git pull origin master, now this will rename file 5 to file 4 because that change is part of Git. Right, so I do that, and now I've got file 4. And the same thing with removing. If you say git rm file name and then push it, that'll delete the file from the repository.
Oh yeah.
Yeah. All right, so things can get out of sync, right? If I make some changes to here, so I change my README on my laptop, and then I go over to the Linux machine, and I make some different changes on here. And I push those over to the repository. So the repository has my real version of the README on it, right? And I come back to my laptop version, and I had made changes on here that I did not push into the repository. Bless you. So if I try to update this, it's going to complain. Okay, what it's complaining about is that I've got changes that I made to my README on here that are going to get overwritten by what's in GitLab. Right? And this is because I made some changes and I didn't push them out to GitLab. And so things can get weird like this. Basically, you've got two copies of your code that are inconsistent with each other, and you pushed one of them to GitLab, and now you're trying to pull that down. It says, hey, you're going to lose some changes you made over here. It won't do that automatically. It'll force you to deal with the situation. So you can do what's called a merge. Merges are kind of tricky sometimes. If you ask it to merge, it'll do its best job of reconciling the differences. So if you added 3 lines here and then added 2 lines here, it'll try to give you a combined version. But a lot of times it just throws comments in saying, hey, do something. So you're better off fixing these things yourself. And you can always start over, right? If I know that this is the version of README that I want, and these are the files that I want, and this is all I care about, right? I can go to GitLab and I can delete that repository if I want, and just say, this is my pristine repository. I'm just going to push this over to GitLab and make a repo out of that.
Push this, and then it would see that README as a different version.
I think so. No, because it knows the changes are still different.
Oh
Right.
yeah, the tip of the range.
But I can go to GitLab.com and I can delete that repository and then just pretend that this is the first time I'm pushing it over. Is an option.
And you don't have to git remote if you delete the repo.
If you delete the repo, git remote is already there. It's already associating this. So you can just git push after that. So as long as you know your code is pristine on a particular machine, right, make a copy of that and then do what you have to do to put it back into GitLab.
Did we need a README for PA1?
No.
Oh, yeah.
READMEs are good practice to create. They're nice in Git because they show up on the front page of the project without having to type them out. And it's kind of standard practice to have READMEs for just describing projects.
But we're doing
But-
that in the comments.
You're doing that in the comment block. Yeah, if I ever need a README for a project, I'll make very clear in the comments, make sure you include a readme.md or something like that. So I don't mind if you put them in, but not required.
And that's not going to mess up your script.
No,
script pulling.
nope, it'll pull down everything. So you can do a denial of service on me if you're mean. All right. So Monday I want to talk about Linux shortcuts, customizing things like PuTTY and your environment and your prompts and so on. Dig into a little more about Linux commands, and I want to start talking about VI. Make sure we get through some how-tos on VI, and then we're going to push back to C and start looking at all things related to C programming.
In the PA2, do you want it named PA2?
PA2 uppercase, yes please. And the executable program called stick.
No, she was just.
All right, I'll see you next time.
It popped up as
And
soon
do
as
you
she